So this thermochemistry is one of the principal applications of thermodynamics in chemistry. So this is the study of heat released or observed during the chemical reaction at certain conditions, for example, constant volume, pressure, and finally the estimate the state function like internal energy or the enthalpy from these certain conditions. So the heat can be measured by using the calorimeter to estimate the internal energy by using this heat capacity or the enthalpy by using the capacity and the constant pressure as well. And I think you know about the exothermic and the endothermic processes. So let me skip this one. Usually like a change in enthalpy are reported for the processes taking place under the set of standard conditions. So standard enthalpy change is a change in enthalpy for a process where the initial and the final substances are their standard state. So this standard state means is that like at the specified temperature and 1 bar, the substances are the pure substances. For example, the ethanol at the room temperature and 1 bar is a liquid ethanol, something like that. And an example of standard enthalpy change is the standard enthalpy of vaporization, which is enthalpy change per mole when a pure liquid vaporizes to a gas. So this one. So in general, the standard molar enthalpy change that accompanies the change of a physical state is called the standard enthalpy of a transition. And we can write the standard enthalpy of transition like with the delta H transition at math. So the vaporization is one of the examples like we saw in the previous slide. And another example is the food fusion, which accompanies the conversion of solid to a liquid. So the important thing to remember for this enthalpy of a physical change is that enthalpy is a state function. So first of all, a change in enthalpy is independent of the path between the two states. And the second, this enthalpy change of the forward process has a different sign with that of a reverse process. So let's see this figure. By the first property, as the enthalpy is a state function, the same value of enthalpy change will be obtained. However, the change is brought about between this initial and the final state. For example, the conversion of solid to a vapor can be pictured either sublimation or a two-step, first fusion, solid to liquid, and the vaporization, liquid to the gas. Because the overall result of this indirect path is same as that of the direct path, so the enthalpy change is the same in each case. Another property is that the standard enthalpy change of a forward process is a negative of its reverse. So as you can see that the quantity is the same, but the direction is different, so the sign is opposite. So if like this forward process is the positive enthalpy of change, then the reverse process will be the minus, like a negative change of enthalpy. And there are two ways of reporting the change in enthalpy that accompanies a chemical reaction. One is a thermochemical equation, and the other one is a standard reaction enthalpy. So let's check the first one. This is a combination of chemical chemical reaction, chemical equation, and the corresponding change in the standard enthalpy. So the change in enthalpy when the reactants in their standard state change to the product in their standard state. So write this chemical equation, then write the standard enthalpy change here like this. So for example, this is the combustion of methane. So the standard value refers to the reaction where the 1 mole of methane in the form of pure methane gas at 1 bar react completely with the 2 mole of pure oxygen gas to produce the 1 mole of pure CO2 gas at 1 bar and 2 mole of liquid water. So at the room temperature and or this reaction occurs at the 1 bar. Another way is the standard reaction enthalpy, which is a molar enthalpy of the species, are multiplied by the stoichiometric coefficient V and summed. So, for example, let's see this reaction 2A plus B becomes 3C plus D. So A and B are reactants and C and D are product. 2 mole of A reacts with the B component, and then they are converted into the 3 mole of C element and D. So the standard reaction enthalpy then becomes like here. As you can see, the stoichiometric coefficient is 3 for C, the product, and then plus the enthalpy change, molar enthalpy for the D, and we are gonna subtract this 2 mole of molar enthalpy A and then B. So this standard reaction enthalpy means that this value is per 2 mole of A and per mole of B and per 3 mole of C or per mole of D. So the thermochemical equation directly ties to this value to a specific reaction as written, while this standard reaction enthalpy express enthalpy change per mole of a reaction under the standard condition and can be scaled. So those are the differences between these two ways. Some standard reaction enthalpies have a special name, such as standard enthalpy of formation, which is the standard enthalpy change to form a compound from an element, this is formation. Or the other one is the combustion, which means that the standard reaction enthalpy for the complete oxidation of organic compound to carbon dioxide and the liquid water. If this compound contains the carbon, hydrogen, and the oxygen, or if there is a nitrogen compound, there will be a nitrogen gas in the product. So, for example, here the standard enthalpy of combustion of benzene is 3,268 kilojoule per mole. So this value means that this amount of heat is released when 1 mole of benzene burns under the standard conditions. So as I mentioned, the enthalpy is a state function. Standard reaction enthalpies can be combined to obtain the value for another reaction. So this application of First law is called the Hassas law. The Hassas law is the standard enthalpy of overreaction is the sum of standard enthalpy of individual reactions. So let's take the example. We are gonna calculate the standard enthalpy of a combustion of propane by using the Hassas law. So yeah, if we know the reaction the complete oxidation of we also know the formation of water from hydrogen gas and oxygen gas. Here. And we would like to know the combustion of propane, so we should first write this equation, this chemical reaction. So this is a propane, and if we do oxidation, we are gonna need the oxygen gas. And for the complete oxidation, the product will be the carbon dioxide gas, and then liquid water. And we need this length. We are gonna calculate the stoichiometric coefficient. So it is easy, there is only 3 carbon here. So we work like this, and then for the hydrogen reactant, in the reactant, the 6 hydrogen exists. So here coefficient will be 3, and then we can calculate how much oxygen we need. So we are gonna calculate the enthalpy change for this chemical reaction with these 3 chemical reactions. So as you can see there, we would like to know this one, and as you can see, this one and this one is cancelled. So we are gonna add the first chemical reaction. Then there will be, and then we want to remove this hydrogen component as well. But here it is the same side, so we are gonna subtract the 3 or reverse of the 3 one. So and we write the reverse of this one. Meaning that it composed of the liquid water to the hydrogen gas and then oxygen gas. And as we study this enthalpy change, the sign of enthalpy change will be changed as well. So if we calculate this one, the first one is and then finally this is the Hassas law, we can calculate the final standard enthalpy of combustion of propane here. Yes. And another example is the formation of CO2 from graphite. So let's assume that we know the standard reaction enthalpy of let me write it. So here, we know the graphite the complete oxidation of graphite and enthalpy of standard enthalpy of a reaction. The complete oxidation of carbon monoxide here. We would like to know is that this one, the partial oxidation of graphite. This is a graphite. So this one becomes the carbon monoxide, and then it is a residual oxygen gas here. So we would like to know standard enthalpy change, reaction enthalpy change. So for this one, we did, we are gonna see these two chemical reaction first, and then now we would like to reduce or remove this CO2, and then let the graphite with the graphite and the carbon monoxide. So what we should do is make reverse of the second chemical equation. Like this. Then if we add the first and the second one, like the reverse of the second one, then CO2 will be removed, and then leave the element that we would like to know, and then this will be something like this. Or we can just learn this from this one from this diagram easily. So like draw the final and the initial and the final state, and then just add some level or a point where like we can estimate the CO and oxygen should be something like here. Then we just can calculate the reaction enthalpy by visually or graphically. So it is just a mathematics, and then check the chemical reaction carefully, then you can get it. Yes, and another standard enthalpy is like we already mentioned, the standard enthalpy of formation. This is the enthalpy change of reaction for the formation of the compound from its element in the reference state. So that the reference state is the most stable state of the element at the specified temperature and 1 bar. So which is a little bit different from standard states. For example, let's think about the carbon. In the standard state for carbon, graphite and diamond can be both, but the most stable state is the graphite. So reference state of carbon is graphite. Like you can see this table. So graphite, the reaction, the standard enthalpy of formation graphite is 0, but you can see that diamond has some number. This means that the graphite is the most stable condition at this room temperature at the 1 bar, and it is the reference state of the carbon. And so another example, like the standard enthalpy formation of liquid benzene at room temperature is like we can write the chemical reaction here. 6 more of graphite. It is the reference state of carbon, and then 3 more of a hydrogen gas, which is also reference state, forming a 1 more of a liquid benzene here. And the standard enthalpy of formation is 49 kilojoule per mole. And as I mentioned, the standard enthalpy of formation of the elements in their reference state are 0 at all temperature because they are enthalpies of null reaction. As you can see, the nitrogen gas. So nitrogen gas is the reference state at the room temperature and 1 bar. So that is the formation. Standard enthalpy of formation is also become 0. And then we can think of how about the standard enthalpy formation of ions in solution. So it has some problem because it is not possible to prepare the solution either cations or anions alone. But this problem can be overcome by defining one ion, conventionally the hydrogen ion, to have 0 standard enthalpy of formation at the all temperature. So, for example, if the enthalpy of formation of HBr is found to be 122 kilojoule per mole, this formation, the formation of chemical reaction, we can write like this. But this value becomes to describe bromide ion only because as we define this formation of hydrogen ion is 0. So you can calculate the other ions with using this definition of hydrogen ions. So there are some examples of standard molecular formation like this. 잠깐 멈추고 출석 부를게요. 오늘은 평소보다 약간 사람이 적은 것 같은데 이유가 있나요? 없나요? So here let's study the way of the calculation of the standard reaction enthalpy with the standard enthalpy of formation. So to get the enthalpy of formation from the reactant to get the enthalpy of reaction from the reactant to the product, conceptually a reaction can be regarded as proceeding by decomposing this reactant into the element in the reference state and then combining those elements into the product. Because the enthalpy is a state function, the enthalpy change is the same however the reaction undergoes. So the value of a standard reaction enthalpy is the sum of this unforming and the forming enthalpies. Because unforming is the reverse of the forming, the enthalpy of an unforming step is the negative. Finally, these enthalpies of formation of the species are multiplied by the stoichiometric coefficients. For example, let's calculate the standard reaction enthalpy of these reactions by the equation above. The standard formation of two products, which is one is the hydrogen peroxide and then 4 more of nitrogen, and minus the standard enthalpy of formation of 2 more of a reactant like ammonia and then 2 more of a nitric acid. So you can check the standard enthalpy formation from any references, and the result is minus 896.3 kilojoule per mole at the room temperature. Then how do we predict the standard reaction enthalpy at the different temperature? As the temperature rises, the enthalpy increases, and standard reaction enthalpies can be calculated from this capacity. Let's see how we can do that. Let me remind you the capacity at the constant pressure was defined by the enthalpy change with the change of the temperature here at constant pressure. So we can, for minute-decimal change, TH becomes the CP, ET here. For the considering change in reaction enthalpy changes with the temperature, we replace this enthalpy with the reaction enthalpy like this, and then we can get we also consider the change of the heat capacity of product and the reactant. So this is the difference between the capacity of product and the reactant. So this is defined like the sum of capacity minus the sum of the capacity of a reactant. This V is still geometric, the coefficient. And if we integrate this one from T1 to T2, our interest temperature is T2. So finally, this integral will become like in the case of this heat capacity does not change, is not affected by the temperature, then we can write this, meaning that it is constant. It is constant. If it is the constant, we can write this equation here. So in this chemical reaction, we know the T1 of reaction enthalpy, we know the CP and the temperature differences, so we can calculate the reaction enthalpy at the G2. Or we can see this with this schematics, that is Kirchhoff's law, which is the result from taking the reaction at T2 and breaking it into the 3 steps here. So as I mentioned, we would like to know this reaction enthalpy at T2. To calculate this, we divide this reaction into 3 steps. This standard reaction enthalpy at T2 is the equal of the sum of these three steps. So let's see one by one. Like here, let's imagine that heat or cool the reactant from a T2 to T1. Then we can use this Cp delta T, which is the enthalpy change, and we also know this heat reaction enthalpy at T1 with using some table or Hassas law, and then at T1 we are gonna heat or cool the product from a T1 back to the T2 using also the enthalpy change is Cp and delta T. So summing these three steps results in the equation where this heat capacity change is the difference in capacity between the product and reactant. So let me write this equation for each step to get the equation here. So this step is first one, this is the second one, and then this is third one. Here, the first one, this is enthalpy change. Changes from T2 to T1, and then the component is a reactant. So the capacity is regarding this reactant, and the final temperature is T1, and then the initial temperature is T2. So the delta H becomes a Cp delta T. And the second one, this is already known. The third one, the temperature changes from T1 at T2, and the component is a product, so we can write this enthalpy change Cp, the product, and final temperature is T2, and the initial temperature is T1. So finally, the enthalpy change of interest is the sum of these three steps. So let me write here. Finally, this one is sum of these one to first, second, and third step. So it will be product. Reaction. This can be written like Cp reaction. Then this is a difference of between the product and reactant capacity. Finally, let's solve this example. Let's see, like 3 mole of oxygen is converted into the 2 mole of ozone. Thus, then the reaction enthalpy is 285.4 kilojoule per mole at room temperature and 1 bar. Then, what is the standard reaction enthalpy at 380 K? So, we would like to know this reaction enthalpy at the different temperature. We first should know the molar heat capacity at the constant pressure for the oxygen and ozone. So they are is like 29.4 joule per Kelvin per mole for oxygen and 38.2 joule per Kelvin per mole for the ozone. And based on the equation that we already studied, we can calculate the change of enthalpy here. So this is the minus 0.97 kilojoule per mole, and finally the standard reaction enthalpy is the sum of this change and the known enthalpy. So it becomes 284.4 kilojoule per mole. So in this chapter, we will learn the thermodynamic principal procedure, the manipulation of equation involving the state function. So state function is important, as I mentioned, is a property that depends only on the current state of the system. For example, enthalpy, entropy, and the internal energy. In contrast, physical quantity that depends on the path between two states are called the path function. For example, work and heat. So let's see this figure. Consider the system undergoing the change in this figure, the initial state I and the final state F. So for the first path, the system expands adiabatically to the final state, then work is negative and also heat is 0. Let's see the second path here, where the initial and the final state is the same as those in the first one, but the expansion is not adiabatic, so Q is not 0. So here work is not 0, Q is also not 0, but the current, the initial and the final state is the same. So the internal energy of both initial and the final are the same, but for path, work, and the heat is different since they are the path function. So for the internal energy, the overall change is the sum of all these infinitesimal changes of the path. Like delta U is the integral of du from initial to final. In this case, we can call this du over u is the exact differential, which is the infinitesimal quantity when integrated gives the result that is independent of the path between the initial and final state. Let's see the heat here. The total energy transfer as heat is the sum of individual contribution at each point on the path. So Q is the integral of dq from I to P, but along the path. So it's important. Here Q is not the delta Q because Q is not the state function. So in this case, we call dq is the inexact differential, which is the infinitesimal quantity that gives a result that depends on the path between the initial and the final states. So the internal energy U is the function of volume, temperature, pressure, as we learned. But the equation of states gives the relation of those three. And that means that if we know the two variables, and we can fix the third. So you can express by two of three variables, such as volume and temperature, volume and pressure, or the temperature and pressure. But for in general case, like a general consideration, we usually use this function of volume and temperature. So we can write here. The internal energy for general case is a function of volume and temperature, and then for infinitesimal changes, we can write the du is del U, del V, constant temperature, dV plus du and dt. If this is just the mathematical definition, I think you learn already in calculus. And as we learned, the heat capacity at the constant volume, this one is capacity. I hope you remember this one. And then we are gonna define this change of internal energy by the change of this volume is internal pressure, which is pi at the constant temperature as well. Then the equation can be written with simplicity. Internal pressure, dV, and then heat capacity here. This internal pressure is a measure of the variation of internal energy of a substances as its volume is changing at constant temperature. And also, it's like you can see the name, it has the same dimension as the pressure. Let's talk about this internal pressure more. So, the idea into the physical significance of this internal pressure comes from the consideration of gas behavior. Let's consider a perfect gas where there are no interaction between the molecules. Then the internal pressure is independent of their separation and independent of their volume they occupy. So this internal pressure of a perfect gas is zero, like here. So the internal energy does not change depending on the volume. But in real gas, molecular interaction becomes more important. For example, if attractive interaction dominates, when the volume increases, the average separation of the molecule increases, and the favorable interaction are weakened. So this leads the increase in the internal energy here, because energy must be supplied to separate these moleculars or to overcome the attractive forces. Just like imagine the gravity. If we wanna lift some object, you are gonna put some work or the energy to lift this object or object apart from the earth. So this explains why internal pressure is positive in this case. You can see the slope of this plot. It is positive in attractive force dominant region. And if the repulsion are dominant here, an increase in volume weakens them, and the internal energy decreases because no energy is required to separate the molecules, implying that the internal pressure is negative here. So you can see the slope is also negative. If here, like we consider like a constant volume, but if we are interested in the temperature dependent change of a U at the constant pressure, so we can write different way. Internal pressure, dV, plus capacity, dt. Then if we divide it, if we divide both sides with the dt, this becomes impose the condition of constant pressure on this differential, then this becomes this is also the mathematics. So we just apply the constant pressure condition in this equation. And we are gonna define the new property, which is the expansion coefficient alpha here. So alpha is so with using this alpha, we can write this equation with a simpler way. Like this becomes alpha internal pressure V plus the C, something like this. So this physical meaning of alpha is the fraction change in volume that accompanies the rise in temperature. So large alpha means the volume of the sample responds strongly to change the temperature. And this equation expresses the dependence of the internal energy on the temperature at the constant pressure in terms of heat capacity, which can be determined in the experiment, and in terms of alpha, which also can be measured in the experiment, and finally in terms of this by the internal pressure. Similarly, there is isomer compressibility kappa here, which is the measure of a fraction change in volume when the pressure is increased. And the negative sign in the definition means that the compressibility is a positive quantity because increase of pressure is a positive, then brings about the reduction of volume, so negative dV, then finally this kappa becomes positive. And let's talk about the change in internal energy at constant pressure for a perfect gas here. So for a perfect gas, the internal energy is zero, as we studied, because the perfect gas does not have a molecular interaction, so the internal energy is independent of their separation. From the equation of from this equation for a perfect gas, phi is 0, so we can write the internal energy pressure, internal energy change with the change temperature at constant pressure is C. This is for a perfect gas only, but as you remember, like the CD was actually the condition at the constant volume. So you can express the heat capacity in a different way for a perfect gas. So with using this equation, there is an easy way to derive the relation between the capacity at constant pressure and the capacity at the constant volume for a perfect gas. So if we subtract this capacity here, and Cp, as you remember, was enthalpy change with the temperature change at the constant pressure, and then this CV, we are gonna use this notation here. And by the definition of enthalpy was U plus PV. So we are gonna use this one here. Finally, we will get this del PV over del T at the constant pressure, and then as you remember, like the PV is nRT for the perfect gas. Then finally, this will become just nR. I think we derived this nR in a previous course. 오늘은 일단 여기까지 하고 한국말로 설명을 좀 해드릴게요. 그리고 출석 이렇게 너무 안 하시면 제가 가끔 부를 때니까 자주 나오세요.